Okay, now let's explore the Nullclines for your classic competition model. You might see the competition model for deer versus moose presented like this, where you have the rate equation for deer as d prime is equal to this, and the rate equation for moose as moose are equal to this rate equation. But I'd like to change the form of the equations by kind of rearranging the terms and factoring them out a little bit so that you can kind of see how it aligns in actual ecological context with what we've learned so far about ecological modeling. Okay, so you can see that in this term we have a d out in front, and then we have also a d squared term. If you take all these d terms here and you match them together, also factoring out the 3, then writing it like this makes it look more like the logistic model, right? So now I can understand what they meant by these two terms by saying that the growth rate is 3 and the carrying capacity is also 3 for the deer. And then we have this interactive term, which is minus md. Okay, similarly for the m equation, if we kind of take just the m stuff here and we factor out the 2 and the m, then we can see again it looks logistic where the growth rate is 2 and the carrying capacity is also 2. They kind of made them the same thing. And then we have this same term here. And remember that for competition modeling, both species are competing with each other so that when they do interact, there's not really a winner because they're both fighting over the same resources. This is unlike the predator-prey model, in which case the prey would be the loser with a negative sign on the interaction term, but the predator would be the winner. So if this is a predator-prey model, really the main difference is that the interaction term here would be positive. Classical predator-prey models actually just use exponential growth instead of logistic growth, but there is an extension of the predator-prey model where you would model individual species population growth with logistic terms as well. Okay, so that's kind of the ecological context. Who loses more when deer meets moose? Just to do a check on, make sure that these equations kind of make ecological sense to you. Knowing that the interaction term is md, but that the d prime equation has minus md and the m prime equation has minus 0.5 md, which one of these species is losing out more? Is at more of a disadvantage when they meet? It's the one with the more negative term, right? So when deer and moose meet, deer loses and moose loses half as much, maybe because it's twice as big. I don't know. Moose is a lot bigger, though. I saw one in Canada once, and a moose is no joke. So anyway, this is a really useful model to study in context of ecology, but let's get to the mathematics under the hood so you can really understand all the different behaviors that this model is capable of. And that's exactly what the technique of Nullclines does for us. And so we're going to start with the Nullclines, where again, I'm going to use the variable on the horizontal axis as a blue-colored Nullcline. The variable on the vertical axis I'm going to use as a red-colored Nullcline. And I already got us started a little bit just by writing out the two Nullclines. Notice the difference between the two forms here. The form that I wrote it in on this side of the board makes it easier to see the context and interpret the equations in terms of what's happening ecologically speaking. But the factored form here makes the mathematics easier. And so when I'm trying to actually get the Nullclines, I would prefer to have it in the factored form so that I can just take that factor and say there's one Nullcline, and then I can just set this factor equal to 0 and get the second Nullcline. So the two different forms have different advantages. Okay, let's get to graphing these Nullclines, and then we're going to try to overlay little pieces of the vector field information on top of them. So in blue, I'm going to draw the D Nullclines. The first one is D is equal to 0, and the D axis is right here. So when D is equal to 0, that's a vertical line. And so I'm just going to draw my vertical line. Like I was saying before, it really is meant to be right on top of the black line. I just drew it to the side a little bit, so it was a little bit easier to view. The second Nullcline is, unlike the predator-prey model where they were all either vertical or horizontal lines, this one is a line which is it's a line with a negative slope, and it has both an x and a y intercept. And so I'm going to have to go back to my algebra days and graph a line. Now, still using that in context of differential equations. Okay, so let's see. M is equal to minus 3D. That would be like y is equal to minus 3x. And so the y-intercept would be 3. And the x-intercept would also be 3. And it has a slope of negative 1. So it looks kind of like that. Okay, supposed to intersect right there. Okay, those are the two D nullclines. Now I'm going to do the two M nullclines in red. The first one's M is equal to 0. That will be just like y is equal to 0, horizontal line going across. Should be right on top of the horizontal axis. I'm just kind of drawing it on top so you can see it better. And then you'll notice that although setting the equation equals to 0 just gives me this statement, I kind of like to solve that statement in terms of the vertical axis variable. That way I can think about it in terms of y equals mx plus b from my past. And so that's why I solved it for m, because m is on the vertical axis. So it's like drawing y equals 2 minus 0.5x. Okay, and so that's a line with the y-intercept of 2 there, and then it has a slope of negative 0.5, which means that I didn't give myself enough room. It's going to go all the way over here and intersect the x-axis right here at 4. Okay, great. And now that I've got my nullclines drawn on, I can easily see the equilibria points, which is everywhere that a red line intersects a blue line. Don't get tricked. Don't pick this point, and don't pick this point over here. It's got to be one of each color in order to have both of these equations being equal to 0 at the same time. So that first point there is going to be the point 0, 2. That's going to be a fixed point. Another fixed point over here is 0, 0, equilibrium point. Another equilibrium point over here is 3, 0. And then finally, we got some mystery point right here. And what the value of D and M in that case would be, the answer would be, I have to solve these two things simultaneously in order to get that actual value. Okay, fine, I'll do it. All right, so let's try to find this value, right, by solving these two equations simultaneously together. So m is equal to minus 3d, and m is equal to 2 minus 0.5d. Okay, and I want these two things to be true at the same time. There's a variety of different ways you can solve two simultaneous linear equations. For me, they're both equal to m, so I guess I'll just set them equal to each other. So 3 minus d equals 2 minus 0.5d. And then I'll bring all the d's over to one side, and so I get 1 is equal to 0.5d. And so I get d is equal to 2. And then once I get the answer for one of the variables, then I just plug it back into either one of the equations. And so m is going to be equal to 3 minus 2, which is 1. Okay, so that is the point 2, 1. Solved it. All right. So that was just to get the equilibrium points, but now the tricky part, we're going to start overlaying either vertical or horizontal vector field behavior on each of the nullclines. Okay. This process definitely takes some getting used to, and is definitely helped by having some fun color pencils or markers so that you don't get too bored. So make sure you get 2 different colors to work with, and let's get started. First, we're going to consider the D nullcline. Okay, on the D nullcline, are things going to be pointing left and right, or are they going to be pointing up and down on the D nullcline? Think about it, right? On the D nullcline, where we got the D nullcline in the first place, is that we set that equal to 0. So on the D nullcline, D prime is equal to 0. Well, D is the horizontal axis, so vector field's not going to have any left or right on the D nullcline. It's only going to be up and down, right? So it's only going to be up and down. Let's just write that out so there's not too many arrows. Only up and down behavior is going to occur on the D nullcline. Whether it's up or down is going to depend on what the sign of M prime is, because this is the thing that still is not equal to 0 on the nullcline for that. Okay, so we're going to do them one at a time. We'll start with the easier one, where the first D nullcline is D is equal to 0, and we're going to plug that assumption into the M prime equation. And M prime is equal to M2 minus M minus 0.5D. Okay, and then plugging in the assumption that D is equal to 0 gives me 2 minus M minus 0.5 times 0. And so M prime on that D nullcline is equal to M times 2 minus M. Oh, geez. That's not always positive or always negative. That depends on the sign of M. So now I have to figure it out again, as usual. A helpful place to start is going to be to figure out where it's equal to 0. You know what's another way that we could do it, just for a little bit of fun, because I know you all love pictures just like I do. If I want to figure out whether this is positive or negative, I could just graph it on the side really quick. Because it's a down-facing parabola. I could tell it's a down-facing parabola because it's minus m squared plus 2m, and it's got roots at 0 and 2. I'm just going to graph this real quick, just on the side to aid my work. It has roots at 0 and 2, and it's a down-facing parabola. So what that tells me is that m prime is going to be positive between 0 and 2, and it's going to be negative when m is greater than 2. That's one way to figure it out. Another way would be to use a method of test points, or use kind of a logical thinking about if m is really big or if it's really little. There's a lot of different ways to win in the plus or minus game, but that's just one little way. And so we can see that when m is between 0 and 2, then m prime is greater than 0. And when m is greater than 2, then m prime is less than 0. That's my conclusion about the nature of the vector field and its up or down behavior on the nullcline for D of D is equal to 0. Oh, look at that. A fixed point. Of course you would switch your behavior at a fixed point. That's what you always do, vector fields. So I'm going to draw the arrows either up or down, and I'm going to know that the up and down switch behavior right at the fixed point, right? So between 0 and 2, it says m prime is greater than 0. So between here and here, I'm going to draw arrows that point up, right? And vertically going up along this nullcline. Remember to draw it just along the nullcline that you're analyzing, because it is just a statement about behavior on that nullcline. Okay, and then once you go to 2 and you go above 2, once m is greater than 2, then the m prime is less than 0. And so then it's going to go down like that. Okay. All right, so I took care of one of the blue lines, and now I got to do the other blue line. Okay, so for the other blue line, I know it's still going to be just up and down behavior, and I'm guessing it's going to be a little bit trickier because now I got this line here to deal with. So let's see. The second nullcline is m is equal to 3 minus d. And the behavior of m is m prime is equal to m times 2 minus m minus 0.5d. What I'm supposed to do is I'm supposed to plug in that assumption. Oh, these nullclines are making me run out of ink. Jeez. Hold on a second. Let me get another pen here. Hold on a second. Fresh ink. All right, let's get back to the nullclines. Here we go. So that's where we left off. Is we're going to plug in the D nullcline that we're working on, which is this negatively sloped line here. We're going to plug it into the m prime equation to see whether we have up or down behavior along this D nullcline. This is probably the most complicated one we've done so far because the algebra is just looking kind of icky. But we know what we're doing, so we're just going to plug and chug along. And so, see how nice and dark that is now? Everywhere I see an m on the right-hand side of the m prime equation, I'm going to replace it with a 3 minus d, because that's the statement for the D nullcline that I'm working on right now. Okay, so this m is going to get replaced by a 3 minus d. And then I'm going to have 2 minus another 3 minus d minus 0.5d. Now I got to simplify that statement. And so we have 3 minus d times 2 minus 3, which is minus 1. And then minus times minus d is a positive d minus a 0.5d, so plus 0.5d. That's about as good as it gets. And so now I have this big complicated statement for m prime, and I'm supposed to figure out whether it results in a positive value or a negative value, and you can see that it depends just on d. I'm going to use a graphical method. There's a lot of different methods you could use, including logic about big and small, or you could use a method of test points. I prefer a graphical method. All I'm trying to do right now is I'm trying to figure out whether m prime is positive or negative, and it depends on d. Lucky for me, I noticed that it's another down-facing parabola in a factored form. So you see, this factor tells me that d equals 3 is one of the roots. This factor tells me that d equals 2 is another root. And the fact that the d times d term has a negative coefficient tells me it's a down-facing parabola. So I'm just going to use this logic for myself, which is a question, how does m prime depend on d? Well, it has one root at 2, it has another root at 3, and it's a down-facing parabola. That's just one of the many ways you can figure this out, but I like it because it's a nice picture. Okay, so what it tells me is that m prime is going to be negative when d is between 0 and 2. Then m prime is going to be positive when it's between 2 and 3. And then m prime is going to be negative when d is greater than 3. I got all that information from the graph, so I'm going to write it down. It tells me that m prime is less than 0 when d is less than 2. It tells me that m prime is greater than 0 when d is between 2 and 3. And it also tells me that m prime is less than 0 when d is greater than 3. Okay, so hopefully you understand why I drew that graph on the side really quick. It was just so I could determine the sign, and then I got all these statements about the sign just reading that right off the graph. Now, looking at my nullcline here and seeing that there's 3 different cases, I can see again that I'm on the right track because the dividing line of 2 and 3 correspond exactly to values of d at equilibria points. You should find that. So it's kind of a nice double check while you're doing your work, is that where the non-zero differential equation flips sign are at the locations of the equilibrium points in the state space, okay? And that's what I got. So between 0 and 2, you see, on the nullcline between here and here, tells me that m prime is less than 0. So I've been using my red pen for that. M prime less than 0 means it's going to go down. So I've got down, 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 like that. But between 2 and 3, it says that m prime is greater than 0. And so I've got up behavior, up, like this. And then it tells me when d is greater than 3, m prime is less than 0. However, remember, I'm only drawing this on the nullcline. And when d is greater than 3, the nullcline falls into the 4th quadrant, which is not ecologically reasonable for me to analyze the 4th quadrant, so I don't even really need to bother with that part. But if I did, I would put some down arrows in there. Okay, but we don't need to work in the 4th quadrant, but that's what that last part's telling you. Okay, cool. So I got through the d nullclines. Now I'm going to do the same exact thing for the m nullclines. Yeah, so I'm going to erase all this stuff, and I'm going to do the same thing again, but I'm going to follow each one of the red lines, knowing that the vector field's behavior will be purely horizontal on the red nullcline. So it's just going to be left or right behavior when I'm doing the m nullclines. It's going to be only left or right behavior. No up or down behavior, only left or right, and that's because m prime, the up or down part of the vector field, is always 0. That's where I got the m nullclines, and the left and right behavior comes from the resulting sign of d prime when I plug in the m nullcline assumption. Okay, let's start with the easy one. M is equal to 0. M is equal to 0. We'll work on this nullcline right here, and we're going to plug it into the DPrime equation. Remember that when you're trying to decide which equation to plug it into, if you pick one and you plug it in and you get 0, that's because you picked the wrong one. That's where the nullcline came from. So you want to pick the other one. M nullclines pick D prime. D nullclines pick M prime. Okay? And so I'm going to plug it into the D prime equation right there. D prime is D3 minus M minus D. Plugging in the assumption that M is equal to 0 gives me this, which says that D prime is D3 minus D. Okay. Well, another down-facing parabola. So if I want to analyze the sign of this, I can do my little trick where I'm asking how D prime depends on D on the M is equal to 0 nullcline. And it's a down-facing parabola with roots at 0 and 3. And so it tells me that D prime is greater than 0 when D is less than 3 and greater than 0. And D prime is less than 0 when D is greater than 3. Of course, there's no need to analyze this for values of D less than 0 because this is an ecological model and we're only working in the first quadrant. Okay, so now I'm going to draw that, and I'm going to draw that with my red pen. Oh, sorry, I had been doing all this work in black before. I'll go back to black for the next one, just because it's more readable. Sorry, I neglected to switch. Anyhow, I'm going to draw left and right behavior because it represents kind of D prime behavior in blue. And this is telling me that I should draw it to the right because D prime is greater than 0 whenever D is between 0 and 3. So all this region right here, I'm saying that it must be going to the right. Okay, and double check worked again because it switches behavior at the point 3, and that is a fixed point. And it's always switching its behavior at the fixed points or equilibrium points. And so now it goes to the left along that nullcline just like that. Okay, now let's go to the more complicated nullcline, and I'm going to do it in black like before so that it's more readable. Okay, so we've only got left and right behavior. Now we've got this nullcline to deal with here, this one like that, and that is the nullcline where M is equal to 2 minus 0.5D. And I'm going to copy down the D prime equation, which is D times 3 minus M minus D. And everywhere I see an M in this equation, I'm going to replace it, don't forget the parentheses, with the statement of the nullcline. Don't forget the parentheses. When you're replacing the M with the corresponding statement of the nullcline, make sure you put in parentheses because then you're going to have to factor through the negative sign. Okay? And so we've got D prime is D times 3 minus 2 is 1. So I guess I could just write a 1 there. And then negative times negative is a positive 0.5. Minus D is negative 0.5D. And another down-facing parabola. So it's going to switch behavior at a special place known as D is equal to 2. Aha! Right at an equilibrium point, just as I suspected. Okay, and so I'm just going to do my little trick again, where I'm just checking the sign of D prime, knowing that it's a down-facing parabola, and it has roots at 0 and 2, and so I get the statement that D prime is greater than 0 when D is between 0 and 2. And I know that D prime is less than 0 when D is greater than 2. Okay, so those are my conclusions, and that is what's going to allow me to draw blue left and right arrows along this red line with the lower slope. D prime greater than 0 means to the right, so in this region of the nullcline, I will draw things going to the right. Remember that this is purely horizontal component. So along this red line, even though this red line has a slope, the vector field itself will be purely horizontal blue lines pointing to the right between 0 and 2. And then when D is greater than 2, it is going to be purely horizontal components to the left because that's the less than 0 region. Okay, I did it! Yeah! There's the Nullcline graph, and it's supposed to tell me something that was worth all that effort, right? So now I really want to think about what it's trying to tell me so I can realize why I am bothering doing all of this. And it's pretty good, actually. It tells me a lot. Like we were saying with the predator-prey model, it divides the state space into different regions, okay? It's not always necessarily going to be 4 regions, but again, in this case, we have 1, 2, 3, 4 different regions, and in each of these regions, the vector field is going to have qualitatively similar behavior. And it's going to be a combination of all the left and right and up and down arrows that we derived with all that analysis. So let's talk about how those are combining, and then that's going to reveal the stability of this fixed point. This is pretty much the most important equilibrium point because it says the species can coexist because both of them are greater than 0. Notice that over here, we don't really want to be here with no deer and no moose in our lives. Nobody wants that. Over here, it says there's just going to be deer and no moose. Over here, it says there's just going to be moose and no deer. This is the only one where we live in the wonderful world of deer and moose. So I wonder if it's stable and attracting other fixed points, or if it's unstable and repelling, or if it's a saddle. I wonder what kind of stability that equilibrium point has. And looking at the Nullclines and then analyzing the different regions that it cuts the state space into will tell us that answer. Okay, so over here in this region as a whole, things are pointing to the right and they're pointing up. So they're pointing up and to the right. So they're basically pointing like that. Now again, I can't guarantee that I know exactly what the slope is. They might be pointing a little bit shallow. They might be pointing a little bit steep. I wouldn't really know exactly what the angle of that pointing is until I decided to state a point and then plug it into the differential equations and get the value of the vector field at that point and then plot the vector. That's what the computer is going to do for me. I'm just trying to get the general idea. General idea is like that way. It's pointing that way. Okay? Now, up in this region, which is the other major region here, we have stuff that's pointing to the left and it's pointing down. And so it's pointing down and to the left. Maybe it's going a little more like that. Maybe it's going a little steeper like that. Maybe it's going a little more shallow, kind of like that. Regardless, it's pointing down and to the left. Okay, and this region right here is pointing up and to the left. So it's pointing up and to the left, so it's kind of pointing like that. And then here it's pointing down and to the right, so it's kind of pointing like that. All signs point to deer and moose. They're both wonderful creatures to have here, and so it looks like we got a stable equilibrium with the values of the specific parameters that we analyzed. The predicted behavior of the system is that no matter where you start, as long as you don't start at one of the other fixed points, any initial condition in the first quadrant that is not already an equilibrium point will tend toward the equilibrium that represents coexistence. So we get both deer and moose.